This video is part of a course on food physics, of which this one belongs to the theory section. This module is about engineering or mechanistic description of food quality. The module before this discussed framework for process physics. So not getting to the quality, but the process itself. That's what was discussed in the earlier module, and the following module after the quality module would be on engineering or mechanistic description of food safety. This video is in 3 parts. In this first part, we're going to discuss just the big picture of what a quality framework is about, and then in the following parts, we're going to get into examples in case of, let's say, nutrients or color, texture, and so on. Now, in each of the examples here, whether it's peas or the French fry or the bread, of course, the temperature history or the temperatures and moisture or the moisture history, they all matter. But the quality that we are talking about is more than just temperature or moisture, obviously. For example, when we're eating the peas, in the very simple way, one of the quality factors can be how much vitamin C does it have, or another quality factor can be how mushy is it, or its color. So quality is multifaceted and is hard to define. It would be crazy to try to come up with one engineering framework for quality. That's not what we are trying to do. We're not trying to address the totality. We will present a conceptual framework to mechanistically and quantitatively describe the most common quality factors like the nutrient content or the color or the texture or flavor. Let's say we are interested in predicting or describing the physics of the color of French fries. And so there are 2 ways to go about this. One is we simply measure the color. And let's say we measure the color here and as a function of different frying temperature. This way we relate the color formed to the temperature, and we can use that relationship. The other approach is thinking of the color formation as a sort of a reaction. So this is the one that is reaction kinetics based. Now in case of color, of course there is such a reaction. As we know, the color formation is described by the Maillard reaction, the rates being dependent on temperature, for example. So the form of kinetics and the rate constant dependent on temperature is going to define the color formation. We can calculate the extent of reaction, that is the color. Now this idea of either direct measurement based or reaction kinetics based, these 2 possibilities, this is very, very general. And so it will apply to other aspects of quality. So let's look at it. So let's say quality, many of these that I'm going to mention in a minute can be thought of these 2 ways, either correlations with direct measurement or some reaction kinetic based models. We are going to start with nutrient. That is the simplest. So nutrient, for example, you can think of just measuring the nutrients, cooking in a certain way and measuring the nutrients. That way we can get the relationship between the 2. But a more mechanistic way would be to think of, let's say, vitamin C as a first order reaction. So we follow the reaction, and then the reaction rate has a temperature dependency, and that's how we're going to bring in the temperature or the process variables. So the same thing for color that I just mentioned. We can do either direct measurement or following the reactions. Same thing for texture and for flavor. So we can do one of these two ways, either measure directly or follow reactions. That's going to be part of our framework. Now, kinetics alone, what we described in the previous slide alone, is not going to give us the framework uh, for quality. And here's the reason. So if we look at this simple heating process on the in here, we can see that the temperature inside this cylindrical mass, it changes in with time, and of course it varies in space, which means the reactions that we talked about, if we take two different locations, in this material, the reaction isn't going to proceed to the same extent, which means somehow we have to bring in these spatial effects. These spatial effects of food processing is fairly obvious. Here's an example where it's very obvious. So it's French fry that is fried, and you see this region is crusty, whereas this is the core that is much softer. So there's spatial effects of spatial variations of quality. There is also time dependence. Of course, the rates of reaction are not proceeding the same way, at the same value over time. So there are spatial effects and time effects. So kinetics need to be combined with process variables like temperature that varies over space and time. They need to be combined to get the full picture of quality. And so that's how we will build the framework. Here we put all the steps together in the mechanistic description of color formation as an example. So local color, of course, is described by the Maillard reaction, but that's going to give color at one location. Now, if the temperature varies, then the color formation is also going to vary. And so we have to combine this uh, local information, reaction at a location, with process. So the process would give me temperature or moisture history, and that needs to be combined with the kinetics. So once we do that, then I get quality at different locations on the food. Now that also is kind of too much information and not exactly how we use it. So we have another step. So in that step, what we do is averaging. So we take information, the kinetics, combine with process, and then average. Okay, and so this is how it looks. So reaction at a location, and then we combined with temperature uh, and moisture history as needed. From there we get description everywhere, and then we need to come up with some sort of averaging. Now this averaging may be trivial in case of color, but for some other quality factors, let's say mechanical property, this averaging is not trivial at all. But so there are different ways of averaging that we will talk about in specific examples. But here we see a complete example of a mechanistic description of color. Generalizing to many quality parameters and building a framework, this quality prediction framework involves obtaining some kinetic information for the quality parameter that can be function of process variables like temperature and moisture. Then we combine that with process variables that can come from the description of process physics, like temperature and moisture coming from, let's say, heat transfer or moisture transfer model. And then final step, we also do some sort of averaging of the quality. In the following slides, we will see detailed example in case of nutrient, color, flavor, and texture.